Welcome everyone, and thank you for joining us for today's webinar titled Advancements in Modern Startle Response Systems. My name is Martin Hess from Inside Scientific, and I will be your host for today's event. Today is session 3. It's the third installment in our Animal Behavioral Neuroscience webinar series. We're happy to share that over 500 scientists from around the world have registered to participate in this web series, and I'd like to extend a warm welcome to those of you who are online with us today. Thank you very much. Our session today is sponsored by Kinder Scientific Company and will provide our audience with an in-depth understanding of the different technological options for measuring startle reflex in rodents. Specifically, our talk will focus on the advancement of the sensing assembly over the years from piezo plexiglass sensors to load cell sensor-based assemblies. Our speaker today is Mr. Michael Kinder, President and CEO of Kinder Scientific, a market leader in the design and automation of behavioral assays for rodents. Michael is also co-founder and VP of Business Development at Auto Science Labs, a company devoted to increasing awareness of and developing solutions for the problems of hearing loss and tinnitus using human startle reflex and animal models. Mr. Kinder has spent 45 years in electronics, chasing electrons as he describes it, with a focus primarily in microprocessor-based industrial applications. He was introduced to automating behavioral assays for research in 1990 and went on to establish Kinder Scientific in 1997. Michael is passionate about startle response technology and will provide us with a wealth of valuable information during today's talk. Throughout the process of planning and organizing this event, Michael has clearly and emphatically stressed the need to educate the scientific community about the underlying technology used in today's startle response systems and how they have evolved over time. So we hope you enjoy his presentation.
So, thank you, Martin. You've created a great venue to help share scientific information, and we appreciate the opportunity we have today. Startle is indeed my favorite assay. It still has so much to teach us. And as you mentioned, today's presentation will focus on the sensing technology used in the assay. That is how we have measured the startle response of rats and mice primarily, because this is the most important, critical part of collecting startle information. It is important to thoroughly understand how this function works. So, a history of the piezo plexiglass sensing assembly and why it's time to move on. What does it actually measure? Is it a true accelerometer? The strengths and weaknesses of the design, and the applicability of load cell sensors and their strengths and weaknesses. First, I would like to thank Dr. Alex Galajuk of Northeast Ohio Medical University for providing some stunning high-speed video of mouse startle responses. What are we after? What measure is it that we're after when we're doing startle reflex? A whole body reflex from a loud noise. So here we have a high-speed video of a mouse startling and to a loud white noise burst, and it's sitting on top of one of our plexiglass piezo sensors. You'll notice in this that the mouse actually becomes airborne, and it's not even touching the sensing plate at one moment. We'll let it run through again. That's when that white light goes off. That's a white noise burst. And his forepaws come up first, and then his hind paws come up, and you'll see that he becomes literally airborne. Now, not all mice startle quite so dramatically, but they're all doing similar things in their reflex. For over 20 years, the piezo plexiglass sensing assembly was the dominant method for measuring startle responses. much of the science on startle reflex stands on the shoulders of this technique. And it is the most widely used transducer technology in the publications to date. So here's a little basic graphic of how the piezo plexiglass sensor actually works. It's a spring, which is one of the plexiglass plate is a spring. It's very important to remember this because it's going to affect the actual data that's collected. So when we first put the animal on the sensing plate, it compresses the plate, the spring of the plexiglass plate. Then we present a loud noise and the animal startles, and it compresses the spring even further. So this adds significant and sometimes confounding complexity to analyzing the data. Actually, inevitably, it causes complexity to the signal. So here's a graphic of a design of a plexiglass piezo sensor where you have the plexiglass plate in gray, 4 feet that hold the corners of the sensing plate, and the piezo disc, which is the actual transducer, is glued to the bottom of the center of the plexiglass plate and typically put surrounded with a protective sealant so that it's protected against moisture. So when we put the animal on the plate, it bends the plate, therefore bending the piezo. So it preloads the spring of the plexiglass plate. Think of this as stored energy that will be released back into the data when the animal startles. Here is an additional amount of force put on the plexiglass plate when the animal actually startles. So when the animal startles, the plexiglass spring is now loaded with the animal mass plus the startle response. This is why the second peak, which you'll see in the next slide, can frequently be larger than the first peak. So here's a display of how we did this 25 years ago, and you can see that all of the values are positive. This is the way we did this back then. And you can see that the second peak is actually significantly larger than the first peak. And that is because the spring is unloading the combination forces of both the animal mass and the startle response. Now, they don't always turn out like this, but they can commonly turn out like this. So when we founded Kinder Scientific, one of the very first things we decided to do was to provide both the positive and the negative values. So this is the same animal, the same response, only with both the positive and negative values displayed. It's clear here that the spring is oscillating. You can see this oscillation, this nice sine wave across the record window. Now that's not the animal response. That sine wave is the resonant frequency of the plexiglass plate. So the sensing assembly is not faithfully following the animal response. The animal response is in this data, but it's complicated by the characteristics of the spring characteristics of the sensing plate. So here's another video of an animal startling, and when this white light comes on, you'll see it come around again. That's when the white noise burst happens, and this is again our plexiglass piezo sensing assembly right here. The mouse cooperated and stayed on the plate for us, and you can see different peaks here, but you'll notice that sine wave is still in this data. So you can see different wave shapes like this, but they all have that dominant oscillating frequency of the plexiglass in the data. So that is inherently the big challenge in using the plexiglass piezo as a sensing assembly. So has the piezo plexiglass sensor outlived its usefulness? what does the output of the sensing assembly actually represent? The output of the piezo plexiglass sensor. It's the combination of the response and the spring, which has been preloaded with the response and the mass of the animal. And something that is dominant in the publications is referred to, the plexiglass piezo referred to an accelerometer. Is it truly an accelerometer? No, this is a misnomer. It's more like a kinetic energy device. You can prove this by taking a mass and dropping it a few inches off of the sensing plate and measure what that force is and double that distance and drop that same mass in. If it were truly an accelerometer, you'd get the same 32 feet per second squared value, because that's actually the acceleration of a falling object. So does the animal weight matter? Something that that question's been asked for decades. People have wondered whether or not does the mass of the animal actually interfere with or get involved in measuring the startle response. Turns out on a piezo plexiglass sensing assembly, it does matter, because it in effect dampens that spring, meaning it changes the characteristics of how that spring's going to operate. So with a piezo plexiglass sensor, the animal mass does indeed get involved in the values. So then we turn to, can we properly calibrate this measurement? An important question. We can, it's possible, but it's with great difficulty to actually calibrate, meaning tie the unit to a standard unit of measure, such as a Newton. So calibrating the piezo sensor is only equilibrating. The piezo transducer produces a DC voltage that's analogous to the amount of bend it experiences. That's the transducer, just the piezo. I'm not talking about here the entire assembly. The transducer is just the portion that creates the voltage. The sensing assembly is that plus the plexiglass plate. However, because the piezo transducer bleeds off the signal so quickly, it only outputs a value when the plate is in motion. This is likely where some of the confusion comes over it being called an accelerometer. But the voltage it creates is not analogous to acceleration, but instead change in distance, how much it's bent. So equilibrating. The definition of calibration is to determine, check, or rectify the graduation of any instrument giving quantitative measurements. Because we're trying to measure the force exuded by the animal, calibrating in volts is not actually calibrating. The best we can hope for in this approach is equilibration. That is, making the sensors from multiple stations produce the same output value for a known input force, or the same station, the same chamber producing the same force repeatedly. So here's one of the more common approaches that's been used, and we did this 25 years ago, to standardize. This is a standardization unit. Here we have a precision DC motor that we can adjust the RPMs to exactly the same value between units. And we have an eccentric weight that we can mount on the axle of the motor. Then we know the exact amount of weight that this object has, and we can drill it in a machine shop so that the hole is exactly off-centered by the amount we want. So this causes a sinusoidal force to be applied, somewhat consistent force to be applied to the sensing plate. Actually, it's rather reliable as long as the weight does not become unglued, as it were, from the axle, or the DC motor doesn't change for some reason in RPMs. So the challenges and weaknesses of an eccentric vibrating motor as a standardization unit: the frequency difference between the plexiglass plate and the revolutions in the motor cause inconsistent forces to occur. That is, they beat against one another. You can actually see this if you have a setup like this, where the dominant graph will show, your wave trace will show the vibrating motor, the eccentric weight, and it'll be a nice sine wave. But on top of that, you'll see the characteristics of the plexiglass plate modulating that signal. So the peaks are going up and down in resonance of the plexiglass plate. So that rather confounds its ability to give you an accurate standardization unit. And there's not much you can do about that, because the spring is going to do what springs do. They're going to oscillate. So it makes it difficult to calibrate to a standard unit of force, such as a Newton. Because the animal weight has a significant effect on the spring characteristics of the sensor, the sensing assembly, one would need a calibrator for each animal weight that is equal to the animal weight. Therefore, it's not practical to pursue true calibration, but rather accept equilibration. It's just not a reasonable thing to try to create a 50-gram calibrator for your mice and a 400-gram calibrator for rats, or a 250-gram for juvenile rats. You'd have to have a calibrator of each weight of animal to be tested in order to truly be able to link the system to newtons. So it's also, the piezo, this is a little different than the eccentric motor. But even with the eccentric motor, it's very difficult to prove linearity on this type of sensing assembly. You can do it statically, but it's a delicate process. You can prove it. They are linear over force, but it's difficult to do. It's certainly difficult to do in the lab where it's being used. So plexiglass, piezo plexiglass sensors, we're stuck with using arbitrary units, such as volts or just a number. Those are not units of measure related to startle response forces, so they're arbitrary numbers. We can link the performance of the plate to a Newton with a single pulse solenoid that is calibrated to a NIST traceable apparatus. This is what we did when we first started providing our Startle systems. We created a single pulse calibrator that we can standardize, calibrate, that is, on a National Institute of Standard traceable load cell. So we know that our standardization unit, our single pulse standardization unit, puts out exactly 1 Newton. The problem is the plexiglass doesn't go along with this, and because of the different weights cause the spring to perform differently, it's still not accurately tied to a unit of measure because of the effect of the animal weight on that spring and the effect of how the spring performs. This was a challenge for us. About 5 years ago, we realized there was still more for us to learn, and it set us out on a mission to accurately understand and profile how piezo plexiglass sensors work. So this is why you should not compare raw amplitudes of different weight animals or even the same animal at different ages when using piezo plexiglass sensor. It's not apples and apples, but rather apples and oranges. So we decided that we had to move to the next level, not because the plexiglass, the piezo plexiglass sensing assembly could not be used, but because it's been my mission from the beginning that we remove all system-induced variability. Startle is infamous for its variability, so it's always been a concern for us as we engineer these devices, what things are being introduced to cause system-induced variability, and we felt this was a significant area that we can improve to hopefully reduce some of that variability and provide consistent, more consistent results. So we moved to a load cell, and what we found with the load cell, it faithfully follows the animal response. It's easy to calibrate because you use static weights. And these weights are easily made NIST traceable. You can send them to a metrology lab. For example, we provide a 100 gram weight, which is equal to exactly 0.981 Newton. So when you put that 0.981 Newton on the system, you adjust the system to 0.981, and this is not a derived or inferred value. This is the way a metrology lab would calibrate any measurement system, and it is a true calibration to a unit of measure and traceable to NIST standards. So it's also easy to prove linearity because you can have, you know, 3 100 gram weights, put one on, get your 0.981, put the second one on, get double that, put the third one on and get 3 times that. So it's very easy to prove that linearity. And the ability to compare responses of the raw startle amplitude responses of different weight subjects now becomes possible. So we could have used this in the beginning and back in 1997, but back then the load cells were rather fragile, at least the ones we were looking at, and they're also very expensive. So we felt like we were sure that we had a warranty issue because you can damage them so easily. And so we shied away from them and stayed with the plexiglass, the piezo plexiglass assembly for its durability. So they've changed the technology considerably, and now the load cells are very durable. You can put as much as 100-pound overloads, so they're very durable. I mean, you can still damage them if you drop them, but they're not as delicate as they were before. So the only weakness we can find in the load cell assembly is it's more expensive to manufacture, significantly more expensive. So here's a load cell. Here's a load cell assembly. This portion is the load cell, and here's the platform that's sitting on it. And you can see, rather like an oscilloscope, this is the voltage coming directly off of the load cell assembly. And notice that there's just a positive going peak and not very much at all negative going. And you'll see right here, that's when his hind paw settles back down on the plate, and his second positive peak is when his whole body settles back down. So this demonstrates to us clearly that the load cell can be designed to accurately follow the animal response. And here we have a system view of an animal response. You'll notice we have that nice single positive peak. We do have a negative overshoot, and there are some overshoots from the load cell, and that has to do with the restrainer that is put on the load cell. You notice from the previous slide, we don't have any restrainer around the animal. He or she was cooperative. We could put them on there once and startle them, but surely they're going to jump off of there, and that was nice how Dr. Galajuk was able to do that. But obviously we've got to restrain the animals, and that's what causes this small overshoot right after this positive response. But we don't really care about that. That's not the animal. The animal data is not in that overshoot, and the rest of it you'll see is very quiet here. And then there's this second one where the animal settles down again. So that's the discussion on our history and the changes that we've gone through, moving from the piezo plexiglass sensor and to a load cell type sensing assembly. In the next section, I'd like to talk a little bit more about the data and some issues with regards to Startle data. Specifically, I want to start with what are commonly called no-stim trials or analog-only trials. And if you look at the graph here, what we have, this display, these pulses here are where we're providing noise bursts and eliciting startle in these blocks right here. These are startle elicitation trials. Typically, no-stim or analog-only trials would be placed in between these trials, right in between the inter-trial interval. There'd be another interval, but from the animal's perspective, they don't see that. So what was the subject doing during these times? is what that analog only, that no-stim trial provides us, an indication of what their activity was in between the startle elicitations. Is that the right question, though? Commonly, this information was used as the baseline activity. So what we're concerned about is the animal in there struggling or causing any information that would cause a question about an individual trial, or is the overall session, if the animal is struggling so much, do we have to care about what that background activity is like? And we would suggest that is not the most important question. The most important question is, what was the animal doing just prior to the startle elicitation? So here he startles at this moment right here. This is a 500 millisecond, a half a second record window. And what we believe is more important is what's happening in this first 250. This is an adjustable window, but that's a lot of information right there. And if the animal is quiet, like this one was, this is a rat response, if he's very stable going into this, what he was doing 5 seconds ago is not exactly relevant to this startle response. What he's doing right here is relevant to what he's doing in a startle response. And indeed, it's only this positive peak as this is a load cell response. It's this information that we care about. Notice how sharp this is compared to this frequency-wise. All of this also has to do with the sensing assembly and how it's responding to the animal response. So we don't care about this. That's not really the startle of the animal. So that's what we'd like to determine the validity of the trial, is what's happening in this 250 milliseconds prior to startle elicitation. To do that, you can do that. You can take two post-session analysis windows. The first window, analysis window, can evaluate this portion and determine whether or not the animal was actually very physically active. And you can do that rather automatically with Excel or some other statistical program. And then you have the second analysis window will focus specifically on the startle response. And again, you can shrink that window, that window B, as it were, to just the area. This is a 50 millisecond wide response area, and we can know just what the animal response was and ignore all this other information that is not really relevant to the animal response. In this window here, we can just analyze the positive only values, ignoring even the negative values, and we'll have just the information that is related accurately to the startle response. So some final thoughts for you. Again, we'd like to thank Alex for his great high-speed videos of those mouse startles. He's using that information in his soon-to-be-released publication in the Journal of Neuroscience Methods, an improved approach to separating startle data from the noise. This work that he's done and he's publishing is actually very related to the presentation today, and I encourage you to watch out for that publication, because those of you that are using piezo plexiglass sensors should find that important information in that publication. Next, I want to suggest to people that they pay close attention to how your system is calibrated or equilibrated and know the difference between the two. Make sure to continually convince yourself that the system is recording the same response for the same known input. It is one of the most overlooked areas of startle research, and if you don't do this, it'll really confound your work. Finally, ask yourself if comparing startle amplitudes of different sized animals matters to you, and decide accordingly.
So, all right, question number one, and I guess, I was thinking about this as you were presenting too. I'm sure you probably get this question all the time, but is it still possible to do good startle research with a piezo plexiglass sensor assembly based system?
Sure it is. It's just that the individuals using them need to make sure that they completely understand the limitations and the caveats that we've talked about today. If you're, for example, as long as you understand these characteristics of the plate and all the oscillation, you can do good research, but you've got to make sure that you're calibrating in a way, or equilibrating actually, in a way that you're convinced that the same force is always giving you the same response.
Okay. Another question here, we've had a few that pertain to PPI, that stands for pre-pulse inhibition, and how does the sensor technique apply to PPI studies?
Well, with any behavioral measure you're trying to do, you want to make sure that, especially if it's measuring force or some activity like that, that you accurately are standardizing the measure. However, PPI is based on comparing the animal's change in response, his inhibition, his reduction of response, to his own startle response. So it's less important in PPI. I would not say it's not important at all, but it is less important in PPI because you're looking at the reduction in response and you're using the animal's own startle amplitude against his inhibited amplitude to figure out what's happened.
Okay, perfect. Can you talk about any other advances that have taken place over the last 25 years in Startle? I mean, you've been doing this for a long time, and you focused today on the sensor assembly, but anything else to add in that regard?
There certainly is. One of the most important things that we've learned over that 25-year period is the auditory pattern of the white noise that's being presented, and in regards to a particular species or strain, because each one of those can have a different hearing pattern and actually a different hearing loss pattern, such as a C57. They start losing their hearing rather quickly. And so if you have white noise that rolls off rather quickly at frequency and doesn't have a solid 16 kilohertz content to it, as that C57 mouse gets older, he starts losing his hearing rather early, and you're going to get different startle responses from that same animal in two different systems that don't have the same 16 kilohertz content. So this is an area where we focused rather heavily, which allowed us to move forward in making startle reflex actually a complete audiogram, a hearing evaluation system for animals. So it's been a well overlooked area, and that's an area of big change in the way startle systems can work.
Okay, great. And I suppose that's information that you could provide to individuals, perhaps on a
Sure.
one-on-one basis. Okay. You focused a bit on the fact that a piezo plexiglass sensor is not an accelerometer in your talk. Why is this so important?
Well, it's just a basic scientific question. As scientists, we really want to understand what it is that we're measuring, and if we don't understand the actual technology, then there's a question of what our understanding is actually based on. So the literature is proliferated with the comment that the piezo plexiglass sensor is an accelerometer. It could be turned into one, just like your speedometer could turn into an accelerometer, but it's not an accelerometer. It does not faithfully follow the acceleration. So it's an important thing to raise, just so that we understand what is it that we're doing.
Okay. All right, we have a couple questions. Pardon my pauses. I'm just sifting through the many questions that are starting to come in. Amy asks a couple of questions. One of them is, can either technology, the piezo plexiglass sensor assembly or the load cell based systems, detect scratching behavior? Is that something you can comment on?
Well, that's more of a, yes, I can comment on that. That's more of a vibration type behavior. So the question is, can we use a startle system that can measure those motor activity type behaviors and tell us what the animal is doing? You can use either of those technologies to record the motor activity that's going on through the entire period that you're recording the animal activity. So it wouldn't be that you would have trials. In that case, you would just continuously record the animal activity, and we actually do that in one of our systems. We use the same technology, and we continuously record that, and we call it a vibration monitor, and we continue, and other systems do this as well. We continually record the forces that are applied to the sensing plate. So the ability to separate, however, grooming from other kinds of motor activity, you can do that. You're going to have to assume that that scratching behavior is rhythmic, sinusoidal, and do some transforms and pull out that information. So that was a long answer. The short answer is
Okay.
yes.
Perfect. And then Amy also asks, with regards to the Startle systems, are you aware of a body of data or some literature with antipsychotic compounds using load sensor technologies?
You know, I know that it's out there. I couldn't quote guide you to those. I could offline. I can get you to that information, but just right here, I'm not going to be able to point
Okay.
to that. I'm sure that literature is out
Okay,
there.
fantastic. And again, just a reminder to everyone that we will answer all these questions and make them available. All right, let's see here. Georgia asks, hi, Michael. In terms of animal weight, they often have people test genetic mouse models where the mice might be sick and smaller compared to a wild type mouse, so different weights. If weight is an important factor with the plexiglass systems, how can they validate the results when comparing two genotypes where the mice are different weights?
Well, that's exactly the challenge. That's the scenario where we're going to get into trouble, because those weights of those two different animals are going to affect how that spring responds, and those two animals theoretically putting out exactly 1 Newton are not going to provide 1 Newton the exact same value coming out of the same sensing plate. That's the point. So that is a challenge. I mentioned Alex Galajuk's paper, and I'm interested to see in more detail when that comes out. There may be some help there from Alex on how to do that. So I'd look for Alex's paper and see if he can help us get through, because that's actually the title of his paper, pulling the noise out, as he calls it, which to me is just the oscillation of the spring. So that is an example of area of concern. That's a good question.
Okay. You mentioned Dr. Galaziuk's publication. Is that something, can we notify individuals when that paper is available and just provide them with a reference?
You bet. If they keep in contact, we'll point them right to it.
Okay.
It's going to be easy enough to find. It's going to be in that publication, Methods, Journal of Neuroscience Methods, and it'll be easy enough to find. And it's coming out. I've been told it's coming out rather soon.
Okay, perfect. Vincent asks, and maybe you touched on this, but perhaps you can just clarify. Some startle systems use cylinders to restrain animal movement during the startle measurements. And in the video that you presented, there was no such restrainer. So, can you talk a little bit more about that, and what are the advantages or disadvantages, I guess, of the two methods?
Sure. First of all, it's pretty well-known study. If you want to stress an animal, put him in a tube. And it's also pretty well established that startle is infamous for its variability. So why do we put him in a tube? Well, we have to restrain him, and it's an easy way to restrain him. So our approach was not to use tubes. We've never used tubes. We used a square box with an adjustable ceiling, giving them some spatial relief above them, but not allowing them to rear up so that we don't get into trouble them trying to fight their way out. This has been shown to be pretty effective in rats. Not so much in mice, doesn't really matter. Put them in a tube, put them in a box, really doesn't matter for mice. But also because Kinder Scientific is so focused on using Startle in an auditory fashion, the plexiglass tube is just not lending itself that well to allowing the sound to get in from all different frequencies in a manner that we would like. So that's another reason we don't use a tube. We have a rather open ceiling type, which has bars on it now for our auditory work. So, I mean, you can use tubes. There's been an awful lot of work out there, and I would not suggest that using tubes is a bad thing. I wouldn't say that. It's a way to restrain the animal and center them over the piezo plexiglass sensor, or if you're using a load cell, the way to center them over that load cell. You do want the animals centered over the transducer, not just the sensor, but the transducer. You want them centered over that transducer. So we stayed away from it for those reasons. It's still a viable way to restrain the animal, just not so much if you're doing auditory work.
Okay, great. That's a fantastic answer. Thank you. Here's a very general question, but what is the most important thing for a beginner to achieve, and what sort of considerations, I guess, goes into starting a startle response type of study?
Well, from our talk today, you can see that I have a big focus on standardizing the system and the chambers so that they produce the same value for the same force. This is really important to get used to it, to understand it, to do it every study, at the beginning of every study. I suggest you do it at the beginning of every day, because there's no reason. It's very quickly done. It really just takes moments, a few minutes to convince yourself that your system is properly standardized, and our new system that it's properly calibrated, because our new system is calibrated directly to a unit of force. But that's very important. Also, just making sure that you start to collect good historical data, because you want to be able to see over time, is something going on with the system, is something going on with your animals that you're being provided. So you really want to have good historical data archives and be able to look at that historical data over time, and make sure that you're getting the same basic results in your controls today as you were last year or 5 years ago.
Okay, fantastic. Thank you for that answer. Going back perhaps to the previous question about restrainers, Caitlin has asked, how restricted should a rodent's movement be while in the restraint?
Well, this comes back to that slide that I showed on, was the animal sitting still just prior to elicitation. So you don't want to have it so open that they're walking around, and mice are little robots. They're not quite as smart as rats, and so you can have a mouse walking across the floor and startle him, and he keeps right on motoring along. A rat, however, this is generalized, it's not 100% true, but you startle a rat and he kind of hunkers down and he's trying to figure out what's going on. The mouse, he just keeps going. So and a lot of it depends on the species and or the strain, but mostly the species you're using. So you don't want so much room in a startle chamber. You don't want so much freedom to the animal that they can really begin to motor around a lot. You don't want them to be able to rear up. You want them to have something above their head that causes them to stop before they can actually rear up very far. I don't like it when I see an animal that their fur is touching all sides of the tube. Because in that situation, when the animal rears up, you saw how that mouse responded in those videos. He became airborne. Imagine that mouse being in a tube and what the sensing plate's going to look like when he hits that ceiling. It's just really going to mess with the startle response. So you really don't want to restrain them so much that they're squeezed against that tube. They need some room to move. So that their reflex is actually not being pressed against the ceiling of whatever the restrainer is. So you do have to restrain them, though. Otherwise, they're gonna motor around a while. Even if you acclimate them there, especially the mice are gonna motor around in there, and that's gonna mess up your day.
Okay, great. That's an excellent response. Let's just ask one more question. Again, for all of those that have submitted questions, if we didn't get to them during the session, we will provide answers after the fact, but we do want to make sure that we end on time. So, Michael, this is from Georgia again. She thanks you for the talk, and I just have to, it's fairly lengthy, so let me paraphrase. She often is asked where to place the analog step in the trial order. And she always tells people to place the analog step immediately prior to the startle pulse. And this is especially true for people running pre-pulse inhibition. She says this to avoid any noise from the animal reaching or reacting to the pre-pulse stimulus. So she's asking if this is the right advice and where is the best place to start recording the animal response.
In a system that does not have dual windows, she's exactly right. So you would classically, in your startle-only trials, put your 50 millisecond, 40 millisecond, 115 dB pulse, and right at that same moment you started that white nose burst, you would start the analog window. And then in the pre-pulse trial, you would also start the window at the beginning of the pre-pulse burst, because you really want to try and make sure that you didn't startle them with that pre-pulse. So in a system that allows you only one analysis window, you do it just exactly as she suggests. But if you have a dual analysis window, you've got this option where you can record a very wide window and use, again, that first quarter of a second, that first 250 milliseconds, and determine whether or not the animal was, active just prior to the startle pulse or just prior to the pre-pulse, and know with certainty what they were doing going into the trial, going into the elicitation portion of the trial. And then the second portion, this next window, can focus specifically on the area that you want to have looking for the startle amplitude, the startle response. So it depends on your system. If you've got a system that has one analysis window, you need to do it as she said. If you've got one that's got two windows, then you got some options that give you more information.
Great. All right, thank you so much for fielding all those questions. There were quite a few, and that was a great Q&A session. What I'd like to do now is thank everyone for taking time out of their day to attend our webinar. We hope you found the information provided valuable. I'd also like to take this opportunity to thank you, Michael, from Kinder Scientific, for your time today and for sponsoring this wonderful event. It was very, very informative. And one final time, I'll just remind everyone that today's webinar has been recorded, and we'll make it available for viewing at insidescientific.com. So please look out for an email from us with links to that resource, as well as links to download the slide deck and the Q&A summary. So with that said, please have a wonderful day, and we look forward to seeing you again at another one of our upcoming Inside Scientific webinars. Thank you so much.